As a result, one end starts to heat up, and the other end starts to cool down. And the reason for that is, when electrons move from one material to another, the energy carried before and after movement is different. Does this violate the law of conservation of energy? Actually, no. When an electron transitions from a high energy state to a low energy state, the energy doesn't disappear. It's converted to heat. This will increase the temperature at the joint. Similarly, when an electron transitions from a low energy state to a high energy state, it also needs to absorb energy from the outside to make up for the energy difference. Obviously, after the heat is absorbed at the interface, the temperature dropped. So how can we increase this effect? Is it like this? This is too low. It was the turn of the 20th century's greatest invention, the semiconductor. Semiconductors have two very interesting properties. One is through doping. We can create electron-rich N-type semiconductors and hole-rich P-type semiconductors. This allows you to simulate two different materials. Second, semiconductors are both good electrical conductors. It can also be a poor thermal conductor. We use semiconductors. We succeeded in creating a device widely known as a pearl nut. Inside it, we connect an N-type semiconductor and a P-type semiconductor in series with the metal plates at the top and bottom. And a current is generated by applying a voltage. At this point, the temperature will rise in the upper half, and the lower half will cool down. Let's analyze this system. Please pay attention. Follow this electron. When electrons pass through the metal, it will have a certain amount of energy. We use it as a reference energy value. As it passes through an N-type semiconductor, since N-type semiconductors are rich in many electrons, low energy orbits are occupied by other electrons. Our electrons would have to pass through orbitals of higher energy levels to get through. At this moment, part of the surrounding heat is converted into this energy for the electrons. This area has lost some heat. The temperature will drop. When the electron reaches the second junction, the opposite will happen. Electrons will enter a lower energy state. Electrons release some of their energy. This energy is converted to heat. This increases the regional temperature. When electrons enter the P-type semiconductor from the metal, since P-type semiconductors lack electrons, our electrons will enter low energy orbits. Again, the electron releases any excess energy and generate heat in the area at the final junction. Electrons need to enter a higher energy state. At this moment, you need to absorb the surrounding energy. This results in a decrease in local temperature. Due to the nature of semiconductors, they have a better thermoelectric effect than other materials. Increase the current without destroying the existing thermal layer. Therefore, the thermoelectric effect can be amplified in practical applications by stringing hundreds or thousands of pull stickers like this. This thermoelectric effect can be maximized. By conducting current, it can become an effective heat sink. At the same time, in order to dissipate the heat from the higher temperature side in time, heat sinks are usually required. Of course, if we connect wires and heat one side, there's going to be voltage in that path, and this voltage generates a considerable amount of current. Then our candle flashlight could finally be invented. But it doesn't have to be that complicated. All we need to do is hold a flashlight like this in our hand.